Just by counting points, lines, and faces, you can tell whether this world is real. One anime used exactly that to prove the existence of an impossible space. Last time, graph theory was born out of the 7 bridges of Königsberg. Today we pull out an even bigger piece of magic. Picture a die in your head. It has sharp corners, edges joining them, and flat faces. Count them. 8 vertices, 12 edges, 6 faces. Now let's do one very simple piece of arithmetic. Take the vertices, subtract the edges, add the faces. 8 minus 12 plus 6, and you get exactly 2. A coincidence? This time a soccer ball. 60 vertices, 90 edges, 32 faces. 60 minus 90 plus 32. And the answer once again is 2. A triangular pyramid or a diamond with tens of thousands of faces. As long as the solid has no holes, the answer is always 2. So where does this number 2 come from? Its name is the Euler characteristic, and its symbol is chi. Hearing it in words alone, you might be skeptical. We've already counted the die, that is, the cube, so let's finish counting the other 2. First, the tetrahedron. 4 vertices, 6 edges, 4 faces. 4 minus 6 plus 4 is 2. Now the octahedron. 6 vertices, 12 edges, 8 faces. And once again the answer is 2. They look nothing alike, yet chi is the same too. That's not a coincidence. That's the signature of a law. Shall we try to break this value? If we chop the triangles of the faces into finer pieces, will chi wobble? Put a single point inside a triangle and that face splits into 3. You gain 1.3 lines and 2 faces. Add up the changes. 1 minus 3 plus 2 is 0. Chi doesn't budge at all. Chi has nothing to do with how you chop the shape up. It is a number carved into the shape itself. So what on earth is it? Now it's time to reveal what that number really is. Let's peel one more layer off the geometry you learned in school. Topology has just one rule. If you can knead one thing into another without tearing it or punching a hole, they are essentially the same. Seen through these eyes, a cube is just a sphere. A triangular pyramid, a soccer ball, in the end they're all spheres. This equation isn't a formula about sharp corners. It's the DNA of space, a barcode engraved with the fact that this is one lump with no holes. And if you punch a hole clean through the middle of the clay to make a donut, astonishingly the value drops straight to 0. An eyeglass frame with 2 holes gives -2. 3 holes give -4. You can already see the rule, can't you? If there are g holes, chi is 2 minus 2 times g. That's the exact relation linking the number of holes to chi. On the left, the sphere gives chi equals 2. The donut in the middle gives 0. As the graph on the right shows, it gets shaved down by 2 each time. Let's nail down one condition. This formula holds only for orientable surfaces, the ones with a clear inside and outside. Because there are surfaces like the Mobius strip, where the boundary between inside and outside vanishes. We'll face that exception in the final chapter. It means that just by drawing triangles on the surface of an unknown planet, you can tell whether that world is a ball or a donut. We don't even need to travel to a planet. This time let's have code count the vertices, edges, and faces for us. With nothing but a list of the triangles that split the surface, you can count the vertices, edges, and faces with no duplicates. For each triangle, the function walks its 3 edges, gathering the vertices into one set, and the sorted edges into another. The sphere was triangulated as the convex hull of 150 points, the donut by wrapping a 28 by 18 grid into a torus. The sphere, 150 vertices, 444 edges, 296 faces. Subtract and add, and it is 2 without a moment's hesitation. The donut, 504 vertices, 1512 edges, 1008 faces. The code spat out 0. Here is what it looks like on the actual meshes. Split them finely or split them coarsely, the value does not change. This invariance shows its power outside the textbook too. It's time for the anime we promised at the very start. In all of subculture history, the work that borrowed this formula in the most distinctive way is The Melancholy of Haruhi Suzumiya. The side story, Snow Mountain Syndrome. Kion and the SOS Brigade are trapped in a mysterious Western-style mansion in the middle of a blizzard. At first they thought it was an ordinary case of being stranded, but the view out the second-floor windows doesn't line up, and the door to the next room opens onto the wrong hallway. Even the stair angles and the room layout are physically contradictory. It's the same eerie feeling as an Escher print, or the non-Euclidean space of the Cthulhu mythos. That's when Koizumi the Esper picks up paper and pen. Rooms become faces and the doors and corridors become edges and vertices. He does by hand exactly the calculation we just did in code, and then he declares something staggering. If chi isn't 2, then this mansion is not a building in an ordinary universe, not something topologically equivalent to a sphere. If chi had been 0, the place would be a topological torus, a closed impossible space where somewhere loops back to somewhere with no way out. Not one drop of blood, not one monster's howl. A masterpiece that paints cosmic horror out of nothing, but an irrefutable mathematical contradiction. And yet a polyhedron with a hole through it really does exist. It's built from just 7 vertices, the Saussure polyhedron. 7 vertices, 21 edges, 14 faces. 7 minus 21 plus 14 is 0. It's a torus. Here's the verdict chart. The tetrahedron, the die and the soccer ball are green, chi equals 2. Koizumi's mansion and the Saussure polyhedron are orange, 0. The eyeglass frame shape is red, minus 2. A single number ignores every outward appearance and picks out only how many holes there are. The Saussure polyhedron has one more feature that raises the hair on your neck. It has no diagonals at all, not a single one. A diagonal is a hidden line joining 2 vertices that aren't connected by an edge. A die has space diagonals and face diagonals. Choosing 2 out of 7 vertices gives 21 ways. And the Saussure polyhedron has exactly 21 edges. Subtract the number of edges from that. 21 minus 21. The number of diagonals is exactly 0. A die has 16 and a soccer ball has a staggering 1680. Yet the tetrahedron and the Saussure polyhedron have none at all. So far, only 2 polyhedra with no diagonals have ever been found. The tetrahedron and the Saussure polyhedron. Whether there's a third, nobody knows. If the tetrahedron is the simplest shape in the world of the sphere, the Saussure polyhedron is its counterpart in the world of the torus. The skeleton of the Saussure polyhedron is the complete graph K7, with all 7 vertices connected. The tetrahedron's is K4. On a plane you can't even draw K5 without crossings. K7 needed a stage of its own, a torus. Now that even the torus has its stage, let's build a bridge from the discrete world of counting points, lines and faces to the continuous. This bridge is made of 2 planks. Descartes, who measures angles, and Gauss Bonnet, who integrates curvature. Every face of a polyhedron is flat. All of the bending sits only at the sharp vertices, condensed down into single points. Descartes saw, a full century before Euler, that this bending could be measured as a missing angle. At one vertex of a cube, 3 squares meet. Each corner is 90 degrees, so the sum is 270 degrees. It falls 90 degrees short of 360 degrees. That missing angle is the angle defect, delta. Add up the defects of all 8 vertices and you get 720 degrees, exactly 4 pi. And 4 pi is just 2 pi times chi. That's Descartes' theorem on total angular defect. The tetrahedron, 180 degrees at each of 4 vertices. The octahedron, 120 degrees at each of 6. Again, 720 degrees in total. We measured the defects of all 3 platonic solids from their actual coordinates and summed them. All 3 come out to 4 pi with no error at all. No matter what it looks like, the missing angles always add up to 4 pi. This is the discrete version of the Gauss-Bonnet theorem. Now let's shave that polyhedron smooth, scattering the sharpness of the vertices across the whole surface. The angle defect that was piled up at points spreads out into a continuous curvature K, and the discrete sum becomes a smooth integral. The result is the Gauss-Bonnet theorem. Integrate the curvature over the whole surface and you get 2 pi times chi. It's staggering. The integral of the curvature is exactly equal to 2 pi times an integer you got by counting points, lines, and faces. A sphere of radius r has curvature 1 over r squared at every point. Integrate it and you get exactly 4 pi. On a torus, the positive curvature on the outside and the negative curvature on the inside cancel out, so the integral is 0, that's 2 pi times 0. Red on the outside, blue on the inside. You can see the 2 curvatures erasing each other at a glance. No matter how much you crumple and dent the surface, the integral cannot budge a hair from the value topology has already fixed. We'll dig into Gauss Bonnet in an episode of its own someday. For today, just remember this. Chi is what bridges the discrete and the continuous. But everything we have set up to this point has actually been resting on one hidden assumption. The Chi formula and the torus test alike stood on the assumption that inside and outside can be told apart, on orientability. That's the condition we nailed down earlier. Give a paper strip a single twist and glue it. The Mobius strip. An ant that walks all the way around ends up on the other side. A surface with only one side. After one full trip around, the yellow normal arrow is pointing exactly the opposite way. You cannot decide which side is up. That is what non-orientable means. Glue this strip shut along its single edge and you get a Klein bottle. In 3 dimensions, you can only draw it by letting it pass through itself. And here Chi runs into trouble. The Klein bottle's Chi is 0. Exactly the same as the torus, and yet it is not a torus at all. For non-orientable surfaces, counting holes with G no longer works. Instead of handles you count K crosscaps, and Chi is 2 minus K. The sphere gives 2, the torus 0, the projective plane 1, the Klein bottle 0. The torus and the Klein bottle end up standing side by side. Chi is a powerful invariant, but on its own it does not classify surfaces completely. It needs one more bit. Orientability. If you were paying close attention, something may have bothered you. That 0 for the Klein bottle was a number we wrote down by hand. Could code count it instead? It is not so simple. A Klein bottle forced into 3 dimensions must intersect itself, and counting it with a convex hull gives Chi equal to 2. To count it properly, we drop down to the 2-dimensional fundamental polygon. Left and right are glued straight across. Top and bottom are glued with a single flip. The grid stays exactly as it is. Only when we wrap vertically do we flip the horizontal coordinate. That way the code is never fooled by self-intersections. Look at the result. For the torus and the Klein bottle, V and F come out as exactly the same counts. The same square, the same V minus E plus F. The only difference is the direction of a single arrow, the one difference Chi cannot see. Now the finale, and the last question is aimed not at mathematics but at the reality you see. We take it for granted that space is flat. But what if the Chi we measure on a cosmic scale is not 2? If the universe's Chi is 0, we may be ants on a torus, or beings living on a Klein bottle with no inside or outside. From the 2 of a die, through formulas and code and impossible space and curvature, all the way to a world with no orientation. It has been a long journey. Chi is a language for reading the structure carved into the skeleton of space, beyond any visual illusion. And at the same time, it is a humble barcode. Great mathematics is not hiding in some grand place. It is hiding in the ordinary act of looking at a single die. Just as the SOS Brigade recognized an impossible space through mathematics, humanity is using this very formula to explore the true shape of the universe. If you enjoyed today's video, please subscribe, hit like, and turn on notifications. See you in the next story.